Hi students. So in last video lecture I gave introduction about plastic analysis of structure, and lastly I completed the assumptions made in fully plastic movement of the section. Okay, so some of the points. So at fully plastic stage, the section will have to obey the following conditions: summation f is equal to 0, then summation m is equal to external bending moment. Summation f is equal to 0 means compression is equal to tension. Okay, so one of the point in assumption is there is no resultant axial force on the beam. That means total compression force is equal to total tension force. Okay, so no resultant axial force. Okay, so they mentioned here compression is equal to tension. Okay, compressional force is equal to tensional force. We all know stress is equal to load by area or force by area. So force is equal to stress into area. Okay, so stress into area. So compression is equal to tension. The compression force is equal to tensional force. So stress into area. So stress into area of tension, that is equal to stress into area of compression. So we are dealing with plastic analysis only. So in plastic analysis we are getting yield stress. So they are mentioning yield stress. So yield stress into area of tension, that is equal to yield stress into area of compression. Okay, so why we are putting yield stress means we are dealing with plastic analysis. So in plastic analysis only we are getting yield stress. So the area in tension and area in compression shall be equal. Okay, so next, plastic moment. We already studied what is plastic moment. The moment corresponding to fully plastified section is termed as plastic moment. Okay, so MP, okay, plastic moment, MP is equal to sigma y into ZP. Okay, so this is one formula. MP is equal to sigma y into ZP. Sigma is nothing but sigma y is nothing but stress. So for stress the unit is Newton per mm square. Okay, for a plastic section modulus the unit is mm cube. Okay, so mm square cube cancel means, so we are getting the unit as Newton mm. Okay, so we are getting the unit for moment. So MP is equal to stress into plastic section modulus, so Newton mm. Okay, finally we are getting the unit of moment. So in this formula, sigma y is nothing but yield stress, ZP is nothing but plastic modulus of the section. Okay, so next, in the above figure, area above the neutral axis is equal to the area below the neutral axis. So this is a figure. So this figure is symmetric in both the axes, not only y axis but also x axis. If we cut the figure in both the direction, in x axis and to y axis, means we are getting equal area in all the axes. Okay, so this is an equal area axis. We are naming it as an equal area axis, and it is also called as neutral axis also, NA, and for equal area axis EAA they are mentioning. Okay, so this is the portion 1 and this one is the portion 2. Okay, for portion 1 the area is A1 and the center of gravity of portion 1 is Z1. Similarly for portion 2 the area is marked as A2 and the center of gravity is marked as G2. Okay, the neutral axis of the completely plastified section is also called equal area axis. Okay, we already saw that. The equal area axis divides the cross section into two equal areas. Okay, so equal area axis means divides the area into two equal areas. The portion 1 and portion 2 is of equal area. That only they are mentioning. These two equal and opposite forces form a couple to resist the fully plastic moment. Okay, so the force acting in both the portions form a couple to resist the fully plastic moment. Okay, so in portion 1 also there is a force acting, and portion 2 also a force is acting. Okay, they form a couple. So compression force and tensional force form a couple, okay, to resist the plastic moment. Okay, so MP is equal to, so moment is nothing but load into distance. So load into distance. So load is equal to stress is equal to load by area. So load is equal to stress into area. So sigma y into A1 for portion 1. Sigma y into A1 into distance is y1. Okay, so y1 is the distance. Okay, the center of gravity distance from the neutral axis. Okay, so force into this distance. Okay, we are taking moment up to this point. Okay, so this is for the portion 1 and this plus. Similarly load into distance. So load is stress into area, sigma y into A2. This is for portion 2. So A2 into Y2 bar. Okay, Y2 bar. Okay, so tensional force into distance. So into Y2 bar. That is equal to, in both these terms, okay, we are taking a sigma y as a common. So sigma y into A1 Y1 bar plus A2 Y2 bar. We are taking sigma y as a common. Okay, so total area of this figure is mentioned as capital A. Okay, so A1 equal to A2 is equal to half of the total area, so A by 2. Okay, so we know that A1 equal to A2 equal to A by 2. So plastic moment MP is equal to sigma y into A divided by 2. Okay, so A1 is equal to this formula. Lastly, we calculated this only, A1 into Y1 bar plus A2 into Y2 bar. So A1 is nothing but A by 2. So A by 2, here also A by 2. Now sigma y and A also common. Okay, so we are taking this sigma y and area as common. So MP is equal to sigma y into A by 2, the whole thing into Y1 bar plus Y2 bar. Okay, and it is written as MP is equal to sigma y into ZP, where ZP is equal to A by 2 into Y1 bar plus Y2 bar. So this is the formula. ZP is equal to A by 2 into Y1 bar plus Y2 bar is equal to, that is nothing but, ZP is nothing but plastic modulus of the section. Okay, where Y1 is equal to distance of center of gravity of the area 1 from equal area axis. Similarly, Y2 is equal to distance of center of gravity of the area 2 from the equal area axis. Okay, so this is also another important 2-mark plastic section of modulus. The plastic modulus of the section ZP is defined as the sum of the first movement of the areas above and below the neutral axis or equal area axis. It is the resisting modulus of the completely plastified section. Okay, so what are the 2 marks so far we saw? Means define plastic analysis, or what is plastic analysis they'll ask, and what is the load factor. Okay, and they'll ask yield moment. Then elastic section modulus. Elastic section modulus is the ratio of moment of inertia to the half of the neutral axis. Okay, so Z E is equal to I by Y, or simply they will denote as Z. Okay, elastic section modulus. Okay, after that when there is when there will be no shifting of the neutral axis, if the structure or the figure is symmetric to both the axis, means no shifting of the neutral axis. Then plastic moment. Okay, so and the assumptions made in the plastified fully plastic section. So these are the 2 important 2 marks, and another one is plastic modulus. So next term is shape factor S. Okay, the shape factor is defined as the ratio of the plastic moment of the yield section, plastic moment of the section to the yield moment of the section. Okay, the shape factor is the defined as the ratio of plastic moment of the section. So plastic moment of the section MP divided by to the yield moment of the section My. Okay, so it is the definition for shape factor. Okay, so we'll know what is plastic moment and what is yield moment. So plastic moment is the moment applied or occurred at fully plastified section is the plastic moment. Okay, so yield moment is the first moment takes place in the plastified section is termed as yield moment. Already we know that what is yield moment. The moment at which the first yield occurs. The moment at which the first yield occurs is called yield moment. So next, so S is equal to MP by Y. Okay, that is equal to MP is equal to sigma Y into ZP. That we know. Okay, already I mentioned here MP is equal to sigma Y into ZP. So MP is equal to sigma Y into ZP. Similarly, My is equal to sigma Y into ZE, or simply they denote a Z. Okay, so that is equal to, okay, sigma Y, sigma and all cancelled. So we are getting ZP by ZE. So it is one more definition for shape factor. So the ratio of plastic modulus. Okay, ZP is nothing but plastic modulus. Plastic modulus of the section to the elastic modulus section. Okay, so this is the second definition. Okay, first definition for shape factor is the ratio of plastic movement to the yield moment of the section, and second definition for the shape factor is the ratio of plastic modulus of the section to the elastic section modulus. Okay, third definition, the shape factor is a geometrical property of a section and it depends only on the shape of the cross section. So it is a geometrical property of the section. Shape factor is a geometrical property of section. It depends only on the shape of the cross section. Okay. Okay, now we'll see a problem for calculating a shape factor of a rectangular section. Okay, so consider a rectangular section. Take a rectangular section. So the breadth is b and depth is total depth is taken as d. Okay, so this section is of symmetrical in both the axis, in x-axis and in y-axis. So the neutral axis NA, and similarly it also forms a equal area axis EAA, equal area axis. Okay, so portion 1 and portion 2, so both the portions are of same area. A1 is equal to A2. Okay, so total area is mentioned as capital A, total area is mentioned as capital A. Okay, so A1 is equal to A2 is equal to capital A divided by 2, we know that. Okay, so they are asked to find a shape factor for a rectangular section. So we know the formula for a shape factor. Shape factor is equal to ZP by ZE. Okay, plastic modulus of section divided by Z divided by elastic section modulus. So S is equal to ZP by Z. Okay, where ZP is equal to plastic modulus of the section. So we know the formula for plastic modulus of section. ZP is equal to A divided by 2 into Y1 bar plus Y2. Okay, so the formula from here only. ZP is equal to A by 2 into Y1 bar plus Y2. Okay, so A by 2 into Y1 bar plus Y2. In this formula we are calculating Y1 bar and Y2 bar. Okay, so Y1 bar is the distance of the center of gravity for the portion 1 from the neutral axis. Similarly, Y2 bar is the distance of the center of gravity from the neutral axis. Okay, for portion 2 and for portion 1. For portion 1, Y1 bar is mentioning, and for portion 2 it is mentioned as Y2 bar. Okay, so Y1 bar, Y2 bar is nothing but d by 4. Okay, so total depth is d, so half of the depth is d by 2 and d by 2. Okay, in this off, okay, it is of equal area axis, so this off of the portion 1. So portion 1 depth is d by 2, so off of the portion 1 depth is d by 2 into 1 by 2, so that is equal to d by 4. So y1 is equal to d1 by 4. Similarly, y2 is equal to d by 4. Okay, so we are putting the value here. So a by 2 into y1 bar plus y2, area A is equal to total area. Okay, total area of the figure. So total area of the figure, rectangle only. So b into d. So b into d divided by 2 into y1 bar. Y1 bar only d by 4. So we are putting the value d by 4. Similarly, y2 also d by 4. So bd by 2 into 2d by 4. Okay, so 2 and all cancel, so we are getting the value as bd square by 4. Okay, so zp is equal to bd square by 4, and then we have to calculate z. Okay, first we calculated the zp and then we are calculating z or ze, elastic section modulus. So elastic section modulus also we know, elastic section modulus is the ratio of moment of inertia to the half of the depth of neutral axis. Already I mentioned. So we are calculating, we are using that formula, z is equal to I by y. Okay, so here I calculated ze is equal to I by y. So I is equal to, for a rectangle section, I is equal to bd cube by 12. So bd cube by 12, okay, into y value is d by 2, bd cube by 12. I is equal to bd cube by 12, y is equal to d by 2. So I am putting the value here, bd cube by 12 into y value, so 2 by d, so cross multiplication and cancelling the value, and we are getting the final value as bd square by 6. Okay, so now I am substituting in s. Okay, s is equal to zb by z. So zp is nothing but bd square by 4 and z is bd square by 6. Okay, so after cancelling this bd square by 4 into 6 by BD square, so BD square and all cancelled, so 6 by 4 we are getting as 1.5. So the shape factor for a rectangular section is 1.5.